Okay, so in this section we are going to talk about the local maxima and minima for a function and its graph. Now, recall from chapter 2, if I have the first derivative bigger than 0 on a certain interval, then I know that f is increasing, because the first derivative is a slope, and if the slope is positive, that means the function is increasing. Okay, and what happened to the first derivative less than 0? Then we should have f is decreasing, right? Because the first derivative is the slope, and the slope is negative, therefore we are decreasing on the function. And we also talk about the second derivative. So if the second derivative positive, we have what? I have positive, so I have plus here, and should be happy face. So this is concave up, right? We have a concave up graph. Now the last one is negative, then you should have what? The sad face, right? Or concave down. Very easy to memorize. Now these four behavior of the function are described by its first and second derivative. Now we can further use the property of the first and the second derivative to describe the behavior of any functions, and in this chapter we'll learn more about that. But now let's take a look at this function. If I give you this function, f of x is x cubed minus 9x squared minus 48x plus 52. Okay, so if you use your graphing calculator to graph this function, can you see the whole behavior of the graph? In other words, can you see on which intervals your function is increasing and on which interval is decreasing, and so on? If you graph it on the graphing calculator, I don't think that you can see it. If you are using the window scale from minus 10 to 10 and also 10 to negative 10 for the y, so if you are using this window only, you will only see something like this. Okay, that doesn't mean anything, because actually this function, the y value is really huge, and 10 to minus 10, this range is not enough to catch the whole behavior of function. Now you have to adjust your window until you can see the whole graph, and sometimes you don't know what range you have to put on in order to see the whole behavior of the graph, and that's difficulties sometimes make you have some incorrect conclusion about the function. Now we will use the first and the second derivative to predict or to see the behavior of the function. If you do use the range from, this is 400, remember this is 400 to minus 400, and this is minus 10 to 10, then probably you see something look like this. So let's go up and down and then up again. Okay, so this point right here, this is minus 2 and 104. It's very huge on the y-axis. This point here is 0 and 52, and this point all the way here is 8 and minus 396. See, the y range is very large, and you have to adjust that correctly in order for you to see a whole behavior of the function. Now, remember, we can use the first derivative to see where the function is decreasing and where the function is increasing. Remember, go back to the previous slide. If the first derivative is positive, then your function should be increasing. If it's negative, your function is decreasing. Okay. So remember that we have the function as what? X cubed minus 9x squared minus 48x and then plus 52. Now use your skill to find the f prime, and from chapter 3 we use the power rule, right? Bring down the 3, subtract 1 from that, and then again bring down the 2, subtract 1 from that, and it should give you this function for the first derivative. Okay, so now our job is to find where this f prime is positive and where it is negative. Okay, so before we do that, let's find the point where this function is 0 first. Now, before you can find where this f prime is 0, we can try to factor this one. So let's factor this. So if you factor this into 2 factors, then you can rewrite this one as 3 multiply x minus 8 times x plus 2, right? So this whole thing here, I factor that into this expression, and I set that equal to 0. And this is easy for us to solve for the x value. If we have this in the factor format, you can solve for x easily. So you can say that x equal 8 or x equal minus 2 are the solution to this function. If you have this format, it's not easy to solve for x. You have to apply the quadratic formula and so on. But if you can factor this out, you set that equal to 0, then you solve for x, which is x equal 8 or x equal minus 2. That gives you the 0 for this whole function. Now we know that these 2 values give you the f prime value to be 0. Okay, so let's plot this on the number lines. Now I have x is minus 2 right here, and then x equal 8. Okay, so this is called x. So now we have x minus 2 and x equal 8 are the 2 points where your first derivative is 0. Now we need to find where it is positive and where it is negative. So the rule is that once you find the 2 points that the first derivative is 0, you should plot this interval. So now we have what? This interval on the right side and the middle interval and the left interval on the left side. So we have 1, 2, 3 different regions. So we have to test in 3 different regions here to see the side of f prime, to see whether that is positive, that's negative, or something else. Okay, so on the left side of minus 2, right, I may pick a random number as long as it's on the left of minus 2. Maybe I pick minus 3. So let's plug in minus 3 to this function, to this f prime, and see what value it will give you. If I plug in minus 3 to this x, f prime, I should get 33. And 33, of course, is positive. So on this region, in this region, on the left side of minus 2, I pick a test point of minus 3. I plug into f prime. It gives me a positive value. That means your function is increasing, right? Your f should be increasing. Okay, now in the middle interval from -2 to 8, I pick another value, another test point to see the size of f prime. Now for easy, just pick 0, right? If I pick f prime of 0, what do I get? I should get, if you plug in 0 for here, you should get -48, and -48, that is negative, right? So if your first derivative is 0, if your first derivative is negative, then your function is decreasing. So f decreasing. Now the last region we want to test is on the right of number 8, and I pick another test point. Now I just pick maybe number 10, right? As long as it's on the right side of number 8, then it's good. So if I sub x equal 10 to here, I guess what? I get 72. So now you can see that this is positive. So f is increasing. Okay, f is increasing. Okay, so take a look at this behavior. On the left side of -2, we have the function increasing. And yes, this is -2. On the left side of -2, we have the function increasing. Now, from the point -2 to 8, it's decreasing. So we have decreasing function until 8. Okay? And from 8 to all the way to the right, we have increasing. And in fact, if you check this graph here, it's increasing back again. So the point, that's the reason that I set my first derivative equal to 0 and I solve for these 2 points. The reason that I did that, because the point where f prime is 0, we have the horizontal tangent line. Or your function, if the function is changing from increasing to decreasing or from decreasing to increasing, it must be changed as the point where your first derivative is 0. Sometimes it won't change, but most of the time, if it's changing from increasing to decreasing or decreasing to increasing, then the point where the size is changing, it must be at a point where your first derivative is 0. That's why I have to solve for the value when my first derivative is 0, and then I pick at those point, and then I pick the test point based on the value I got from that. So the point where my first derivative is 0, the point where I solve here, are called a critical point. Okay, so if I give you a function, I ask you to find a critical point, you have first to find the first derivative and then set that equal to 0, and then you solve for the value. Okay, now the methods, we are using the first derivative to decide where the function is decreasing or increasing. We call this as the first derivative test. Now we can also use the second derivative. Now remember, if your second derivative is negative, you have the concave down. If it's positive, you have concave up. Okay, so I already have my first derivative here. Now let's try to find the second one. So f double prime. So we just take one more derivative after the first one. So bring down the 2 to 3, give you 6x, and then -18, and this constant becomes 0. Now, again, when you get your second derivative, you also have to set that equal to 0. So if I set 6x minus 18 equal to 0 here, I solve for x, it gives me 3, number 3. Okay. Now, I draw that on the number line again, x number 3, right? and then I have two different intervals. One is on the left of 3, the other one on the right of 3. Now let's pick the region on the left of 3. I pick 0, right? So f double prime of 0 would give me minus 18, right? If I plug in 0 for x, it gives me 18, minus 18, less than 0. That means on this left region is concave down. And on the right of 3, I pick somewhere maybe 4, right? So f double prime of 4, 6 times 4, 24, 24 minus 18 is going to give me 6, right? 6 is bigger than 0, so this is concave up. Okay, so in fact, if you take a look at the function around here is point is 3, so we have 3 and minus 146. So from your second derivative test, on the left side of number 3 we have concave down, and in fact, yes, this is 3 right here. Now on the left of 3, that means in this region we have concave down, and on the right side of 3, which is from here and to the right, we have concave up. And yes, our prediction is correct. So your first derivative should tell you where your function is increasing, decreasing, and your second derivative test should tell you where your function will be concave up or concave down. And the point here, the point that you got the maximum value on here, this is called the local maximum. That means in the area of this point, this value is the highest value. In other words, it is the tip of your curve where you have the concave down. Okay, so the tip point of your concave down function here should be your local maxima. So local maximum really it's just to describe that around this region, this point is the biggest value. This point is not the biggest value of the whole function, because you have this point here all the way to the right. This point is of course higher than this point. Therefore, this point may be the maximum of the function, but this point is the local. So the word local means that it's only maximum in this area around this point. The same thing here, you have the local minimum, where you have the minimum value of the function around this area region only. Now, the local minimum usually occur where you have the concave up, and the local maximum is occur where you have the concave down. That's it. Okay, let's move on to one example. So before we move on to another example, make sure that let's take a look at this picture. Right. So I have the function here. I have this point is a point P. Okay, and of course in this region, in this point we have the horizontal tangent line, or we have f prime of P to be 0. So f prime of P to be 0, that is a point where we have a tangent line, and this point is a point of changing between decreasing to increasing. And here you have what? You have f prime to be negative because it's decreasing, and on this area we have f prime to be positive because this is increasing. And in this case you have what? Local mean, because this is concave up and you have a minimum here. Now similarly, this point, this graph, the same point here, point P, this is the local max because it's concave down. And again, on the left side is increasing because your slope is positive, or your first derivative is positive, and on the right side your first derivative is negative or decreasing. Okay, and if you do your second derivative, then concave up should give you the positive value for your second derivative, and it should give you negative value for concave down. And if you plug in, there's one more thing to note, that if you plug in the value of P for your second derivative, if it gives you a zero value, if it gives you zero, then the test won't tell you anything. If it gives you something positive, you know it's concave up. And if it is negative, it tells you that you have concave down. But if it's zero, then it won't tell you anything. Okay, so make sure that when you do the testing, if they give you zero, then we cannot conclude anything from your second test. Okay, if you are watching this video, make sure you email me by this Friday, and I'll give you 1 point to your midterm score. Okay, so let's go to some examples about this topic. Okay, so I have a function f of x equal x cubed minus 9x squared minus 48 x plus 52. Okay, and we want to see what happened at a point x equal 8. So at a point x equal 8, do we have the concave up or down? Okay, so if they ask you to check if this is concave up or down, then you should use your second derivative test. Now let's try to find the second derivative first. So the first one, again using the power rule, bring down the 3, subtract 1 from that, bring down the 2, subtract 1 from that. Now continue doing the same thing, you get the second one, bring down the 2, 6, subtract 1 from that, and this is 18, the constant becomes 0. Now set this equal to 0. This is actually the same function we talked earlier. So set this equal to 0. I have no, actually I don't have to do that because they already give us the point to test for. So I just plug in directly to that. So if I plug in x equal 8 to this function, I guess what? 6 times 8 is 48 minus 18. That's give me 30, right? So 30, because this is positive, I should have concave up, right? Now if they ask us for another point x equal minus 2, then I do another testing for minus 2. Minus 2 I plug in here, I got minus 12 minus 18, that's minus 30, and this is less than 0, or you have concave down. Okay, So that's really all we have for the example. It's pretty straightforward. Now let's try another example. Okay, so another example. Now they want us to graph the function f, and this function has the following behavior or features. So the first one is we have the critical point when x equal 2 and when x equal 5. The second here is f prime positive to the left of 2 and also positive to the right of 5. And the last piece of information they give us is f prime is negative between 2 and 5. Okay, so let's see. I don't know the actual value of this function, but I can draw the general shape of this function, where the function is increasing, decreasing. Remember the critical point. So recall from your previous example, how did we find a critical point? So we find a critical point by setting your first derivative equal to 0, and then you solve for x, and those x are called a critical point. Now we have 2 and 5 to be your critical point. Okay, and usually the critical point at a point where your function is changing from increasing to decreasing or decreasing to increasing, because at those points your first derivative is 0, or you have a horizontal tangent line, because your slope is 0. That means you have a horizontal slope or horizontal tangent line. Now we already know that 2 and 5, so we have this region, right? We have 1 region, 2 region, and 3 region. Now we know that f prime to the left of 2, that means in this area, and to the right of 5 in area. So in this area and this area we have f prime bigger than 0, right? Or the function should be increasing, and less than 0 in between 2 and 5, that means decreasing. Okay, so I can draw something like this, maybe increasing right up to this point and then stack to decreasing, and then from this point we can increasing again. This is the general shape only, the behavior. So because this is increasing, we have the positive first derivative, then decreasing, and then increasing again. Okay, so at the point 2 and 5 we have horizontal tangent line, because this is 0 for the slope. And this point is a what? This is the local max, and this point is the local min, right? Because the local max is only occur when you reach when your function is increasing and then decreasing, that means you are reaching to the maximum value. And when you're decreasing and then you're increasing, where your function reach the minimum value. Okay, so these 2 points are called the local max and local min in this area and this area only. In order to find the maximum value beside the local max and min, you have to check at the 2 endpoints, because if there's an endpoint, then this point should be the max, not this point. This point is only the local to this local area, not the whole function. Now there's a warning. Usually we set the first derivative equal to 0, and we solve for x to find a critical point, and this point usually is the point where your function is changing from increasing to decreasing. But sometimes not every critical point, so not all the critical point give you the local maximum or local minimum. Okay, so not every critical point will give you the local max or min, and we can see that's why. Now, if you consider this function, this is y equal x cubed. If I find y prime, it's going to be 3x squared, and I set it equal to 0. I solve for x, it gives me 0, right? Which is this point. So if you take a look at this function, this is increasing, and then to the left of that is increasing, and also to the right of this is also increasing, right? So of course, in this function, this critical point is not a point where the function is changing from increasing to decreasing. It's increasing all the time. So make sure that you do pay attention. Not every critical point will give you the local maximum or the local minimum, as in this case. And this is a good example. Okay, let's go to one last example. Now, if I have a function f of x equal to x squared plus bx plus c, okay, this is what? This should be the parabola, right? And we're gonna find the critical point. Now you want to find a critical point. First, find the first derivative first. So using the power rule, bring down the 2x, and this is just 1, right? So bring down the 1, subtract 1 from that, give you b. So you set this equal to 0. So for x, so 2x equal minus b, x equal minus b over 2x. I mean x equal minus b over 2. And in fact, if you have your function plot here, this should be the parabola. And remember, the parabola, it has what? It has the vertex, and the vertex here is minus b over 2. So your critical point is the point where you get the vertex or the local minimum from the critical point. Okay, so that should be the end of section 4.1, and I'll see you in the next video for section 4.2.